Okay, why don't we go ahead? Are there any questions today? Next week, Sterl Finney will begin a series of lectures on the astrophysical phenomenology of gravitational wave sources. So this will be our last week, at least for a while, of dealing with the formalism for gravitational waves. And he'll begin to apply some of the simpler things that we have done in terms of formalism to specific sources, but the whole character of the course will change for a while as we pretend we're astrophysicists and try to think like astrophysicists instead of like relativity theorists. Today at 4:10, that is after Mark Wise's class, the TAs, I guess, and I will, or at least I will be available in the interaction room, the lounge in Bridge Annex between East Bridge and West Bridge for discussion of material from the course. So I strongly encourage people to come to the discussion, particularly if you have any questions or are having any problem with the material. What I'm going to do today is talk about interaction of gravitational waves with material through which they propagate. And I'm going to treat the special case of propagation through a homogeneous material, which is quite different from what you deal with in gravitational wave detectors. In gravitational wave detectors, a key feature of the detectors is that they are inhomogeneous. They actually wouldn't work very well if they weren't inhomogeneous. And so when we come to talk about the detection of gravitational waves, it'll be a rather different story in many respects from what we see here. But what I want to do here is to get a feeling for how strong and what the nature of, how strong is and what is the nature of the interactions between gravitational waves and material through which they propagate. And as we'll see, the interactions are extremely weak, so weak that they're unimportant in any astrophysical context. We'll see that quite quantitatively in a series of examples. So the foundation for the discussion is that we have a homogeneous medium, and I will treat several examples. The examples will be a medium just made of dust, a perfect fluid, a viscous fluid, an elastic medium, and a medium made of a cloud of neutron stars or other mechanical oscillators. So I'll go through all those examples. But this is to be a homogeneous medium through which the gravitational waves propagate. And I want to analyze the propagation in Lorentz gauge. And so I want to look at the equation which says that the wave operator acting on the trace reversed metric perturbation is equal to minus 16 pi times the stress energy tensor. And the stress energy tensor I'm going to be concerned with is the stress energy tensor associated with the waves themselves perturbing the medium through which they propagate. And so that perturbation in the stress energy tensor caused by the waves then acts back on the waves through the wave equation. Now, I want to, right from the beginning, focus on the physically measurable pieces of the waves, which means the transverse traceless part of this trace reverse metric perturbation. And so right from the beginning, I want to simply take the TT part of this on both sides. In the special case where I am going to take the waves, are plane waves, propagating in the z direction. And so taking the transverse traceless part merely means that we throw away the temporal part, we throw away any components along the z direction, and we focus on components in the x and y direction, and remove the trace of those components. And so I can write this equally well then as the wave operator acting on h bar jk, transverse traceless. The process of taking the transverse traceless part, I can pull that inside the wave operator, because all that process does is it just throws away everything except the x and y directions, and pulls off the trace, which also satisfies the wave equation. And so I can regard this then as just the wave operator acting on, in fact, the gravitational wave field that we introduced originally by defining it in terms of the Riemann tensor some time ago. That's going to be minus 16 pi times, you take the stress energy tensor associated with actually the perturbations of this homogeneous medium, and you take the transverse traceless part. That is, you only look at the x and y components and you throw away the trace on them as well. So this is the wave equation that we'll work with, and I don't need the bar on top, because having taken the transverse traceless part, the bar doesn't do anything for me. It's a trace reversal, and if I have no trace, then whether it's barred or unbarred doesn't matter. So this is the wave equation that I want to work in terms of. Let me say I'm going to give you some reading that corresponds to this material. The reading is much more mathematical and does this with considerable mathematical care, but I'm going to give you a treatment of it which I believe is fully intellectually honest, which is far simpler than what you will see in your reading. The reading is from a unpublished manuscript of a book that I was working on in the 1970s, and I put it on the shelf, or 1980s, I guess it's probably an 87 or 89 version. I put it on the shelf in order to get other things written, and I've never picked it back up again. But it's the only place I know where you'll find the subject I'm talking about today treated sort of all together, but even it treats it in a much more complicated way than I'm going to give you today. Okay, so let's begin with the first example, and that is a medium that is made of dust. And by dust, I just mean particles that exert no non-gravitational forces on each other. So it's like a fluid, but with vanishing pressure for the fluid. Now, in this case of dust, since the particles exert no forces on each other, each particle is going to fall freely. And I presume that the dust is initially at rest before the gravitational waves pass, at rest in the reference frame that we're working in. And so as the waves pass, then each particle is going to move in the manner that is described, that we have treated before for freely falling particles. Now, so let me talk about, in order to deduce what is the perturbation of the stress energy tensor, let me look at what the motion of the dust particles look like in the local Lorentz frame of some arbitrarily chosen dust particle. So I introduced the local Lorentz frame, which is different from the different from the Lorentz gauge that I'm using up here. So I'm going over looking in a different reference frame than the reference frame in which I have written down this wave equation. But the reason I want to do this is that this stress energy tensor is really something that is gauge independent. And so if I can understand it in the local Lorentz frame of a dust particle, it's going to have the same value in this coordinate system, which is very nearly the same as the local Lorentz frame of the dust particle, but it differs by perturbations of the metric that are of order h. Okay. But the stress energy tensor being gauge independent, it changes by fractional amounts of order h when you go from this reference frame where the wave equation is written down to this local Lorentz frame. So it's going to be essentially unchanged. So in the local Lorentz frame of any dust particle, the motions of nearby particles are just the motions that we talked about before. For the plus polarization, if this is the y-axis and that's the x-axis, the particle I've chosen, my fiducial particle, remains at rest in this local Lorentz frame, but particles down on the x-axis, they move out, and particles on the y-axis move in. Particles on the minus x-axis move out, and the particles here move in. And so there's the lines of force that are producing these motions are lines that have the standard quadrupolar form. And so the directions of motion are like that. Now, this motion is a shearing motion. That is, the material over here is moving like that, the material over here is moving like that, and so it's a pure shearing motion. There are no volume changes, just a shearing of the material like this along that direction, and like that along this direction. But as the wave oscillates, what happens is these guys move back and forth like this, these guys move back and forth like that. But there is no restoring force because these are dust particles. And so there are no material stresses build up as a result of those motions. These particles all just move happily. Each one thinks it's freely falling, but there is a net shearing motion as seen in this local Lorentz frame. There is, and so TJK has a piece that would look like rho Vj Vk, where these are the velocities as seen in this reference frame. But this is something that's second order in the motions, or second order in the amplitude of the motions, because it's two velocities. The motions themselves are linear in h, because h is the thing that's pushing things around, as seen in this reference frame. And so this is something that's second order in h. It's of order h squared. And so it's totally negligible in magnitude, and we can ignore it. And besides that, there's no contribution to the stress tensor associated with the motions of the dust particles. And so at first order in H, the perturbation, let me put a delta on here. This is the perturbation due to the gravitational waves is the only part I'm concerned about. The steady stress energy tensor associated with the background is irrelevant for the gravitational waves. It's only the oscillating part that's going to couple back and alter the gravitational waves. And so the statement is that delta TJK is of order h squared. At order h, delta TJK transverse traceless is equal to 0. And so therefore, the dust has no influence on the waves. The waves propagate through the dust, satisfying the vacuum Einstein equation. Any questions about that? Okay, so now let's look at a second example, the example of a perfect fluid. Now, for a perfect fluid, I claim that the fluid motions are identically the same as what we had in the case of dust. And the reason that that is the case is that these are pure shearing motions, and a perfect fluid exerts no force to prevent pure shearing motions. Perfect fluid means there's no viscosity. So there's no resistance to shearing. If there were some volume change, then there would be some resistance induced by these waves. There would be resistance to that. And the result would be that there would be a coupling between sound waves, which have oscillating volumes, and the sound waves in the fluid and the gravitational waves. But in general relativity, the gravitational waves produce purely shearing motions with no volume change. And so there's no way to couple to the fluid, no way to, for the fluid to exert any kind of a force in response to the shearing motion that it's undergoing. So once again, in this case, the perturbation in the stress tensor is 0 at first order in H. And so there is no influence on the wave propagation. There are theories of gravity in which the gravitational wave produces a dilatation in the transverse direction. So if the wave is propagating from me to you, there is a polarization state that is an expansion transversely and contraction. These are theories where they're in addition to, or in place of, the usual general relativistic spin 2 gravitational wave field. There's also a scalar field. An example is the Brans-Dicke theory of gravity or other scalar tensor theories. And in these theories, the dilatation in the transverse direction and no motion along the longitudinal direction in these theories, that dilatation then would try to make the volume of a fluid element change, and there would be some resistance to that when you tried to compress the fluid element or expand the fluid element. And so there would be a coupling of the gravitational waves to the fluid, but not in general relativity, because the character of the gravitational wave force is a purely shearing character. Okay. So again, no influence at all. Now a viscous fluid is different, because in the case of a viscous fluid, there is a resistance to shearing motion. And so in the case of a viscous fluid, we need to look at that resistance, and that resistance is going to give us a contribution to the perturbation of the stress tensor that will be first order in the gravitational wave field. And so we will get a non-trivial propagation through a viscous fluid. Now in a viscous fluid, the perturbation in the stress tensor is going to be equal to something that is proportional to the rate of shear. Now this rate of shear is a quantity that one introduces in fluid mechanics that some of you are familiar with, but others will not be, that basically tells you, that measures the strength of this shearing motion. And it has removed from it entirely any issues of the rotation of the fluid or any issues of volume changes. It describes only shearing motions. And that there's a tensor called the rate of shear tensor, sigma jk, that describes that. Or it's actually called just the shear by a fluid mechanician. But if you're going to also do, as I will do, elasticity theory, then I want to distinguish between the rate of shear and the static shear, which is the rate of shear and its time integral, which I will call the shear. So there's something called the rate of shear that I will explain what it is in a moment. But the statement is that you learn in fluid mechanics is that there is a resistance to shearing motion that shows up in the stress tensor in the form of a term in the stress tensor that is minus twice the coefficient of viscosity, eta, times the rate of shear. So it basically counteracts, it tries to counteract the shearing by throwing in a stress that is just proportional to minus the shear tensor. Now, what is this shear tensor? It is the antisymmetric part of the velocity of the fluid, take its gradient, then compute the antisymmetric part of it. So you take these slots and you invert them, and then you take a factor of 1/2. And so that's the definition. And this antisymmetric part, the symmetric part, I'm sorry. The antisymmetric part is the rotation. It describes the rotation. The symmetric part, you then also want to remove the trace. So it's minus 1/3 VK, let me call it VL/L times delta JK in a nearly Cartesian coordinate system, which I'm using. Okay. So it is the symmetric trace-free part of the shear tensor. Now, In our particular case, we're going to compute this rate of shear in the local Lorentz frame of a fiducial fluid element or a fluid particle, because the local Lorentz frame is the frame in which we can think of everything in physical terms. And so we can use all of our non-relativistic intuition in a local Lorentz frame. So that's where I want to compute it. And in that local Lorentz frame, the motions that I'm concerned about are these motions induced by the gravitational wave. And I'm going to claim, and we will see that it is the case, that although shearing is going on in just the manner that I talked about, and although the stress tensor is building up resistance to that shearing, nevertheless, there are no net forces acting back on any fluid element to counteract the shearing motion, which may seem a little surprising, though you can see it from this diagram that this fluid element that was our fiducial fluid element, and it could be any fluid element you might want to choose, the fluid elements up here are trying to drag it in that direction by viscous forces. But the fluid elements down here are trying to drag it in the opposite direction, and because the whole pattern is symmetric across that plane, there's no net dragging force. And similarly here, the fluid elements up here are trying to drag it in that direction. The fluid elements down there are trying to drag it in this direction. There's a balance, and there's no net dragging force. We'll see that mathematically in a few minutes. But this is then an explanation for why, when computing the velocities, I'm going to assume that all these particles, again, are moving just like free test particles. They're undergoing just the motion that they would if there were no forces between the particles, even though there is a viscous stress force between the particles. And so the statement is that the motions the fluid motions are unaffected by the shear stress, delta TJK. So that's my assertion based on this physical argument. And so just adopting the result of that assertion, then we know that a fluid element at this location will undergo a displacement, delta xj, that is given by the standard formula for freely falling particles of 1/2 hjk transverse traceless with 2 time derivatives on it. No time derivatives, because this is the displacement, not the acceleration, times xk, the position of the fluid element. So here's xk, and this is delta xk, the perturbation in the position. That means that the velocity of this fluid element, Vj, is just delta xj time derivative. The initial velocity vanished. The only velocity we have is due to the gravitational waves, so I don't need to put a delta on this v. Vj is delta xj time derivative, or it's 1/2 hjk transverse traceless with a time derivative on it, times xk. So that means that the gradient of the velocity field, as seen again in this local Lorentz frame, the gradient of the velocity field is 1/2 the gradient of this. Let me make it Vj/L. 1/2 then h dot jk tt, partial derivative of xk with respect to xl, which is just a Kronecker delta. And so that's 1/2 hjl with 1 time derivative on it, transverse traceless part. Okay. This quantity, in fact, is already symmetric. What we're asked to do when we compute the rate of shear is we're asked to symmetrize it. But it's already symmetric. As you see from here, it's the gravitational wave field is symmetric in interchange of its 2 slots. And it's already trace-free because, well, this is the TT as a TT quantity, so it's trace-free. And so that tells me immediately that sigma jk, the rate of shear, is just 1/2 h dot jk transverse traceless. So a very simple result for the rate of shear. And I can now put that back in to this expression and see that the perturbation in the stress energy tensor caused by this shearing motion, or by the gravitational wave, is minus 2 eta times h dot jk transverse traceless. And I can then put that back into the wave equation and wind up with a wave equation that says box hjk transverse traceless, which, because these waves are propagating in the z direction, is minus dt squared plus dz squared hjk transverse traceless is equal to minus 16 pi times delta tjk. And now I'm not really terribly worried about factors of 2, but I guess I ought to go back here and note that I have this factor of 1/2 that cancels that factor of 2, and then there's a minus sign. Oh, I guess the minus sign remains, but this factor of 2 is not there because this 1/2 cancels that too. Okay. And so this is equal to then, this minus sign cancels that minus sign, and it's 16 pi times the coefficient of viscosity times one time derivative acting on hjk transverse traceless. So this then is a wave equation where the influence of the viscosity is to introduce a first time derivative of the gravitational wave field on the right hand side. So I'm going to leave it as an exercise for you, a very simple exercise, to see what this says about the wave propagation, and to see that, in fact, what this first time derivative term does is produces attenuation of the waves, so that the gravitational waves become weaker and weaker as they propagate, so that they attenuate as h going as e to the minus z over some attenuation length. And so, and I will leave it to you to derive that attenuation length. And that attenuation length that you will get is just equal to 1 over 32 pi eta. Well, that's not a very enlightening formula unless you know something about viscosities. Okay. And so let me tell you about this coefficient of viscosity. So what I'm going to tell you is something that you learn if you go study fluid mechanics or statistical physics, if you take Physics 136, for example. You will learn that if you have a model for what's going on, which is a model that works under a huge variety of circumstances, where your material is made of particles, and these particles are usually atoms, but in the case of turbulence, these particles can be large turbulent eddies in the fluid that behave like particles. But is that how you spell model? L-E? I don't know how you spell model. It's made of particles that travel individually for some distance, some mean distance, let me call it S, which is the mean free path. And then they collide with each other and get knocked into a different trajectory. So under those circumstances, it is these particles that travel for some mean distance S, then collide, get knocked on a different trajectory, then travel some mean distance S, then collide again, They are responsible for transmitting forces between here and here. There may be a collision over here, and then a particle travels over to there and then collides, and it carries over to here information about what is the mean rest frame of the material over here. Statistically, it does that. And so this material over here discovers the mean rest frame of the material over here is one that's moving like that relative to the material over here, and so it experiences a force that tries to drag it back. And that all comes about as a result of these collisions. But these collisions then communicate across distances that are of order the mean free path. And so not surprisingly, the coefficient of viscosity gets bigger the larger the mean free path, because you can communicate more effectively across from one region to another. It also gets larger the faster the particles move. They can communicate more easily if they move faster. And so this coefficient of viscosity turns out to be of order the mass density times the velocity, which is a momentum density basically. This being transported, I'm sorry, this is different from that velocity. The mass density times the mean particle velocity inside the material. Which will be of order the speed of sound under most circumstances, times the mean free path. So that's a sort of a standard formula for the coefficient of viscosity. Now there's another important thing to know, and that is to thinking about this mean mass density. It's the mass density of all of these particles that are running around in the material. This mass density rho generates space-time curvature, because it's any mass density generates space-time curvature. Okay? And so I want, just in order to have a clear and simple picture in my mind, I want to just think about the space-time curvature that's generated in the simple case where I imagine this medium is all, at least momentarily, at rest. It's neither expanding nor contracting, and so I'm not talking about a piece of the expanding universe, or if I am talking about a piece of the expanding universe, it's in the case where the universe will expand and then recontract, and I'm talking about it at the moment of maximum expansion. Okay. Just to in order to think about it in simple terms, I've got a static then universe, and in that case then the Einstein equations for the background curvature, so the Einstein field equations for the background curvature of space-time. So this is a side discussion in order to get some feeling for that attenuation length for background curvature of space-time. They say that the Einstein tensor is 8 pi times the stress energy tensor. Now the Einstein tensor is of order in magnitude 1 over the radius of curvature of space-time squared, because the Einstein tensor is just a contraction of the Riemann tensor, then with a trace removed, and so it's basically proportional, or in magnitude, in characteristic magnitude, it's roughly the magnitude of the Riemann tensor of the background space-time. This, let me put D on here, this is the background space-time curved up by the viscous fluid that I'm dealing with. And so the 1 over the radius of curvature of space-time squared is equal to 8 pi t mu nu background, and the dominant piece of that is going to be the mass density. So that's of order 8 pi rho. So if I want to talk, and in this case where the universe is not expanding, where it's, say, a static universe, this curvature is basically the spatial curvature. So I can think of myself as having a closed universe, like the surface of a balloon that has some radius of curvature r, and that radius of curvature of the closed universe is in magnitude related to rho in this manner, or rho is 1 over 8 pi r squared. So this is just to get a simple picture out in our minds about what's going on. We have a fluid that is filling the universe. It curves the universe. The length scale of that curvature is related to the mass density in this way. Now, in the case of our own universe, which is expanding, when you go through cosmology to figure out, in that case, what does this radius of curvature mean, it's basically the Hubble distance. So it's the size of the observable universe in that case. Our universe is very nearly flat, and so spatially, in fact, it isn't closed up like this. The dominant parts of the curvature are associated with warpage of time, basically, in our expanding universe, not with warpage of space. But it is true, as you might have thought, as you might have expected, that when you go through the treatment of the cosmology of a universe like our own, that the mass density in the universe looks like this, where the r that appears there is approximately the Hubble distance, 10 to the 10 light years. Okay. Or in time units, the Hubble time, roughly the age of the universe. Okay. So an interesting thing to do is to compare the attenuation length with the radius of curvature of the background space-time, the background radius of curvature that is produced by the same viscous material is producing the attenuation. So you imagine you have a universe that's just filled with this viscous material. There's nothing else there. It's curving the universe up. The radius of curvature is related to the mass density of the material in this way. And I want to compare the attenuation length of gravitational waves moving through this viscous material with this radius of curvature of the universe produced by the fluid itself. And so I want to look at the attenuation length then divided by the radius of curvature of the universe. That's going to be 1 over 32 pi times eta. And the radius, and then 1 over r. And then for eta, or for 8 pi, let me start over again. For eta, let me put in the rho, the mean particle velocity times the mean free path. So I have 1 over r, 1 over 32 pi rho, the mean particle velocity, and the mean free path of these particles that make up the fluid. Now, 1 over 32 pi rho, that piece is just r squared over 4, and 4 at my level of accuracy is unity. Okay. And so this just looks like r squared over r times the mean particle velocity times the mean free path. Okay. Or it's r divided by the mean free path and then 1 over the mean particle velocity. And so we want to ask ourselves, well, how big can the mean free path be? Well, the very concept of viscosity makes sense, and the whole analysis makes sense only if the mean free path is less than or of order the inhomogeneity scale on which the shearing is occurring. If these particles have a mean free path that is enormous, far larger than the wavelength, and that inhomogeneity scale in our case is the gravitational wavelength. So if these particles have a mean free path that is huge compared to a gravitational wavelength, they're going to head from here over to there, and the gravitational waves have oscillated a number of times in the meantime, and there really is no significant communication and no significant shear stress build up. And so this formula really makes sense, or to put it differently, the viscosity actually reaches a maximum when S is of order the reduced wavelength of the gravitational waves. And when the S gets bigger than that, this analysis fails. You can still talk about an approximate stress tensor. That approximate stress tensor gets weaker and weaker as S gets bigger and bigger beyond the reduced wavelength. In fact, you can plot as a function of s, where this is the reduced wavelength, what is the magnitude of the shear stress. And it goes up linearly with s and reaches a maximum there, and then it falls. Basically is 1 over s. And so the best we can do is to have a material whose mean free path for the particles is of order lambda bar. So the conclusion is that S is less, in this formula, eta is the maximum when S is of order lambda bar. And so that means that the quantity I'm computing is less than, is greater than or of order R over lambda bar times 1 over the mean particle velocity. So that's always going to be greater than or of order 1, because even if the mean particle velocities get huge, they can't get bigger than the speed of light. And if you have waves that have a reduced wavelength that gets as large as the radius of curvature of the background space-time, you don't even have waves anymore. Waves make sense only when the reduced wavelength is less than the radius of curvature of the background. And so under essentially all circumstances, under all practical circumstances, this will be very big compared to 1. So that means the attenuation length due to viscosity is really very large. There is negligible attenuation when the waves propagate for a distance of order the radius of curvature of the background space-time, where that radius of curvature is produced by the viscous fluid that's trying to do the attenuation. So attenuation is never, at least for viscous fluids, it's never of any significance. So there's a classic calculation looking at the issue of attenuation using particle physics techniques for attenuation in the very early universe that was done originally by Zeldovich and his group in Moscow in the early 1970s. And what they show, and I'll give you the reference so you can go read this in the assignment sheet that I'll pass out on Wednesday. They show that if you go back in the extremely early universe where the temperature is extremely high, and the gravitational waves are really beginning to behave more like particles than like waves, you look at graviton interactions with other particles, they show that the attenuation length, or that the amount of attenuation is negligible going all the way back to the Planck time when the universe was born. The attenuation just barely starts to become significant at the Planck time. Or in astronomers' language, the optical depth becomes of order unity going all the way back to the Planck time. The optical depth is negligible for any looking back at the early universe toward the Big Bang at any time any later than the Planck time. So this simple example then gives an analogous conclusion to what Zeldovich's analysis does for the very early universe. Okay, any questions? Yeah.
Gravitational waves do interact with our gravitational wave detectors, and
yes, but not very well. We wish they would interact better. We would love to capture them entirely. That would give a huge, strong signal. So there is some attenuation. This attenuation length is not 0. It's awfully, awfully small.
But it's still large enough so that we can see them.
It's large enough that you can see them using the technology of the present decade, but not using the technology of the 20th century. Using early 21st century technology, we are sure we can see them. But it requires an enormous effort with the highest technology that we have available because the interaction is so weak. You might ask, in terms of energy conservation, where does the energy go if the waves do get attenuated a little bit? They're dying out as e to the minus z over the attenuation length. Well, the answer, not surprisingly, is that the energy just goes into heating the viscous fluid, viscous heating. And you can show that rigorously, but that's pretty obvious. That must be where it is going.
Just for my information, what is the amount of energy that is interchanged between the gravitational waves and the LIGO?
So I will let you calculate how much energy is interchanged between the gravitational waves and the LIGO. It's so what you want to do is calculate how many. One way to do it is calculate how many gravitons are absorbed or exchanged, and then use the energy of one graviton. Now, in the case of LIGO, well, let's hold this off. Things are a little bit subtle. In the case of LIGO, there's no viscosity, except for a little bit of optical viscosity associated with the interaction of the masses with the light that is bouncing back and forth between the mirrors. There's negligible viscosity, and so thinking in terms of absorption of energy is not really the fruitful way to think about LIGO. But for bar detectors, which we will talk about also later, that can be a fruitful way to think about it. Yeah. In the case of a bar detector, the waves can actually deposit energy in the oscillations of the bar and change the normal mode, the amplitudes of the normal mode oscillations of the bar. In the case of LIGO, you're basically moving free masses back and forth and watching how they move. And so it turns out, in the case of LIGO, thinking about it in terms of energy absorption is not a terribly useful way to think about it. But that's for later. Okay, I next want to talk about a different kind of medium, about an elastic medium instead of a viscous medium. So why don't I go back over here.